Okay, so now back to the exercise. Exercise 5, the first, we go and do the direct design by putting these notches, make a band stop notch filter with certain sampling rate, and basically to reduce, for example, line humming on your data. And yeah, impulse responses, that kind of things. Then basically the fourth one, I think this is quite close to the FIR, the exercise. Exactly, but now you need to design an IIR filter. Hey, wait a minute. Yeah, let's compare it with the your FIR design. Then again, you design, actually first try to parameterize your filter properties basically on the FIR exercise, and then design an IIR high pass filter with the basically same property. Oh no, that was the what I'm talking about. So IIR band high pass filter. This is just a design. So low pass, high pass. Yeah, okay. Then IIR filter, same as on the FIR filter. Comparison, then again, same. I think did you already have this one? The 3-band equalizer on FIR. I don't remember. Well, but anyways, there's a kind of design, a equalizer, 3-band equalizer, very small, very basic one, meaning the tone control with us the discant and bass, or treble and bass. It also has a middle. Did it? No, okay. Yeah. Maybe I should actually draw you a graph what I'm looking for on this 9th exercise. Yes. Cam. Okay, it fits here. 5.9. Human ear, 20 kilohertz, the maximum frequency. And then basically the normally, if you put this one on bass, middle, and treble or discant, whatever that is called, depending on the continent, you basically have 3 different filters there. One, the bass filter is a low pass filter, the treble or discant is the high pass filter, and the band pass actually is more for middle. And the tone adjustment is very simple. You just add some gain to those bands and mix. So basically the system looks like this. There. Ta-da. So 3 systems, the outputs are just summed together. Or if you have same order system, you can sum the filters, coefficients, do the calculations only once. Okay, but now I should show you something with the MATLAB. All right. Some graph windows, just let me close the graph windows. There we go. So IIR filter design, And we start with this notch dot stop and filter. Stop and bend. And a couple of parameters, for example, on say measurement systems, we could have a sampling rate only something like 1 kilohertz. For example, 1,200 samples per second. So this would be some measuring systems. Okay, and we have the line humming there. At which frequency? What is the most distinct one? The frequency there? No. Yes. Yeah, double the yes, double the 50 hertz. The rectifier actually does it. In here, it's the light rectifier basically which does it. There's no negative light coming out. Have you noticed? The negative cycle still have the positive light, so it's rectified. Okay. Anyhow, so we have the this noise frequency is 100 hertz. That's common in Europe. Line humming. There. Of course, nowadays we also have all sorts of other humming sources with higher frequency because of the switch power supplies. Okay, but there we have the sampling rate and we have the FN. We can now start designing the filter. Right. So basically, the corresponding frequency for this line humming is 100 hertz divided by 1200, or actually, let's do it like this: Fn divided by Fs times 2 times pi. That's the angular frequency of 100 hertz. And at this frequency we have notch, meaning the 0 on unit circle. So z equals exponential of omega n times, well, j of course, and then the actually times j and minus j. So that gives us complex conjugate pair of zeros which are exactly the unit circle. So z plane of zz. There we go. So we have the 100 hertz signal is right there, I believe. Yes. Okay. Now we need. Yes. Yes. I and j are actually imaginary units here. You can always overwrite both of them if you want to, so, which is fairly simple to do by using single letter variables. Okay, you can overwrite functions. You can overwrite exponential, for example. So, well, it gives. Yeah. J is for engineers, I is for physicists. Okay. I or J, who cares? Okay, so now we have the zeros at the right place, and let's take a quick look at the system parameters. So system coefficients for this one would be polynomial divided by these zeros. So these are the system coefficients, and now we can actually calculate the also the frequency response of this one, just to make sure that we have everything at correct place. Yes, exactly at 100 Hertz we have a lot of attenuation. Unfortunately, also the rest of the amplitude response looks a little bit bad. So it has some gain on the on higher frequencies, and then, well, it's just ugly. But it reduces the line humming. All right, then let's take a design parameters for that A, meaning the half width of the filter. For example, half width of the filter could be 20 Hertz. Nah, enough. Nudge. So the corresponding angle is there. And that's the same as the distance of pole to the unit circle. Pole equals to 1 minus omega hw times the exponential of something, but we already have it. It's on the same angle, so we just multiply it. It's basically just the distance changes. There, poles, and the let's see the z plane again. There, those are the zeros and pole locations. Ooh, and then the filter coefficients, polynomial defined by pole locations, and finally, oops. There we go. Nice design. Almost unity gain. That's close enough for me. And there, basically, let's take a quick look at. I would say it's about 20 dB. I should take this one out somehow. Plots, not plots, figures. Oh, there are the tools. There we have. Seeing is believing, so 20 dB, minus 20 dB and plus 20 dB, so it's about minus 3 dB point here and here. So yes, we have the notch filter, subband notch filter as designed. Okay, just two parameters. One, where's the notch, and then another one, how wide is the filter. Oops. There. Then the hard part. Different filters or these digital filters. I would start with say this classical filter design. There's nothing wrong with classical filters. And these are basically analog and then by linear transformation. And let's take a look at the doc. document of butter, for example. Ooh, that's good. So basically we just need to give it the order number and the cutoff frequency as normalized cutoff frequency, and here the normalized cutoff frequency actually means times pi. Okay, meaning that basically the scaling factor or the cutoff frequency and the real cutoff frequency. Okay, I'll give you an example. So let's see. B U dot AAU ABU. Okay, there. Order number, for example, fourth order, WN is the normalized cutoff frequency, and in here, for example, 100 Hertz, and you divide that one by Nyquist frequency. That should give the cutoff frequency at the right place, but we'll see. So this is the filter design, simple like that. Let's make this not C plane. Frequency response, BBU, ABU. Yep. That's the fourth order Butterworth filter. It has fairly flat passband and then not too steep transition band, and the cut frequency is right here. Okay. Okay, if we had a design that we have to have the attenuation at 300 Hertz, at least 60 dB, then there's also a function but_ord to call to find out the whoops, lots of stuff here. Calculate the order number for the filter. Oh, that's nice. It also has the reaches the lowest order n of the digital button for this filter, but with no more than RPDB on pass band rip. Wow. Okay, that's mathematicians think that there is a ripple on Butterworth filter. It doesn't have ripple. It's rippleless filter. Okay. But anyways, I think that one defines the design point. Okay, those values there are passband, stop band, passband ripple, meaning in this case it's actually the no ripple, and stop band ripple. So it finds the n that fits into this box. Let's try it. So all right, so BBU, oops, not that one, NWN. equals mod ord. There. Passband starts at so that was the 100 hertz, right? Did I put 100 hertz on that? Maybe. Okay, divided by fs divided by 2 there. Okay. Stop band, for example, at 300 hertz. Decibels 3 dB in here, and stop band attenuations, for example, 60 dB. Sixth order, and then that's the design cutoff frequency for that one. Yep. Yes, 60 dB at 300 hertz, and then yeah, the 3 dB point is at 100 hertz. Okay. Basically, you can do the similar kind of designs also with the Chebyshev one and the elliptic. They all have the similar helping functions. So let's see, but odd, Cheb 1 odd. Yeah, there. One odd would be used with the Chebyshev one filter design subroutine. Okay, and elliptic also. You can play with those. Then there's also, let's see, what else do we have here? There's also nice package on these computers. Basically, you can also, if you want to, you can use some of these design subroutines. Design filter designs any filter, IIR, FIR. You just need to give it parameters, and it does everything for you. Then I will also show you, although I know that some of you are working with the Octave, which does not necessarily have all the functions. It had the Chebyshev bezel butterworth, so this exercise definitely can be done with the also Octave. But since we have this very expensive MATLAB, we also have very expensive tools like FDA tool. Did you know? Oops. Let me see if this one shows up. Okay, desktop. Alrighty, that's how you design a filter. So low pass filter, for example, let's make it IIR maximally flat, for example, and then we just make here the sampling rate, oops, cutoff frequency 100 hertz, design filter. Things for a while, and then you get this kind of maximally flat filter, or, well, there are all sorts of nice filters that you can actually play with. And okay, different order numbers. What does it do? And yeah, so that's a perfect tool to play with and design filters. It's not required though, since all of these exercises should be also be able to be done with the Octave or other, say, similar packages. But since we have the MATLAB, well, use the tools. One tiny hint on using this one, how to get these parameters, since I want also to, some of these pictures there. If you want to, let's see, export. Well, where is the export, was it export? Okay, there. Clicking export, you can get the coefficients of these filters to the MATLAB workspace. All right, but actually right now it goes there as the second order system matrix. We haven't gone through that one yet. It will be on the next week. But anyways, you can get the parameters. You can take a look at the parameters here. Zeros and poles, step response, impulse response, group delay. Everything is here. So why I'm showing you this one now? Well, just because. I'm evil. All right, but
does MATLAB have any built-in optimization tool that you can just show that I want these parameters for my filter and compute it for me?
Yeah, well, you just basically can build it here. It's just, click the correct parameters here and you get whatever you wish to. Yep. All right, so that's my part of the show. Have fun.